Hi, I'm going to go through the solutions for this quiz. I think it might help you a little bit if I explain some things, but of course you don't need to watch this video if you don't want. So the first one, it says, what I'm trying to do here is have you look at the concept of Six Sigma and kind of translate that into what exactly are they talking about when they say Six Sigma. So I have this, when we produce ball bearings, the outside diameter is normally distributed. The mean is 2.5 millimeters and the standard deviation is 0.003 millimeters. How many parts per million, ppm, will on average fall 6 standard deviations either above or below the mean? So what I'm going to go down here because this is a normal curve and it's not exactly related to that problem, but what it's talking about is if I can go out 6 standard deviations, and these marks here are 2.25 and 2.89 standard deviations. So what I'm doing is I'm actually having like way out here 6 standard deviations this way and 6 standard deviations this way. And you know that this is asymptotic, so it actually never crosses 0, so there's always going to be some values way out. And what I wanted you to see is on a two-tailed test, so either above or below, I wanted you to see, well, how many parts per million, how often, if I have it happening a million times, how many of those times will be 6 standard deviations apart. So actually, I just used a Z calculator on online because it's not really something you can calculate yourself. You could, I guess, we have the equation of this line, and so what we could do is we could use integrals to figure out what the area under this curve, because that's above 6 or below -6. So we could do that. We don't usually use calculus to do it, but we could. But instead, there's a Z calculator, ZNP calculator that I found online, where I just typed in 6 for the Z value, that's 6 standard deviations, and it said that it was P is equal to 9.855 times e to the -10, which an inverse of that is 1 billion. But now what I'm thinking is I think I have this wrong, because I think that that's a one-tailed test. Now, I think I should probably look that up, but this could be just this is a billion, about 1 in a billion is 6 standard deviations, but that might just be above. It might not be a two-tailed test. So it could be 2 in a billion or 0.002. So I think I need to double check that, but I'm hoping that my little mistake possibly didn't mess up your understanding of it. I'm just asking, how often do things fall way out here? So the next two are just like discrete and continuous. So the first one is the number of defectives in a lot of 10. So there's 10 possible, could be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. No, it could be 0. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It can't be 2.5, so it's not a continuous variable. It's discrete, either 1 through 10. So that's why it's discrete there. And this, on a survey, people can only answer this, or this. They can't, if we put numbers on here, they can't enter 1.5 on that. So it is a discrete variable. So on this one, I'm asking you to think of, well, we have this 5.9.2, the height between these two, how many, what proportion of men, what's the probability of a man, what's the proportion of men, what percentage of men, that's all the same way of asking that, fall between 5.9 and 5'11". That 5'9" and 5'11", that's the question. So the way you do it is you find the Z numbers here, and so I converted 5.9 to a Z value by taking the difference between 62.2, and this is the mean, which is given here, divided by the standard deviation, which is given here, and that's 2.25, a Z value of 2.25. A Z value is also the number of standard deviations, right? So if you look at between here and here, there's 2.5 standard deviations between those two, and a standard deviation is 2.8. I hope that makes sense, because this is the number of standard deviations. So that means that 98.78% fall below that value. And then I did the same thing for 71 inches, and I found that 99.81% fall below that value. So below this is 99.81, below this is 98.78. So I took the difference in those two, which is going to be this. That means only 1.3% of the men, Okay, I think I'm back. I think my dog's done barking. Sorry about that. I wanted to ask you about this notation where mu and x bar. What's the difference between those two? Mu is a population value and x bar is a sample value. Now, I know probably you've had this explained to you a million times, but usually we don't know mu. We don't know mu and sigma, which are indications of the population's values, the mean and the standard deviations. We do know x bar because that's the average of the sample. So this is a mean value or the average value of us. This is of the sample, this is of the population. And so what we're always trying to do is sort of estimate what the population is. Not always, but often we're trying to estimate what the population is given some kind of sample. So in this next one, I asked you to look at all this data and try to figure out what is the mean and the standard deviation. The mean, all you do is calculate the average of this. I copied this and brought it into Excel, which was kind of not nice of me because you guys can't do that. You don't have the electronic document of it, but that's what you could do. And then you can also do a standard deviation function. So those are the values, the average and standard deviation. And then I asked you to create a histogram. This I created in SPSS, but I wanted you to go through the thinking process of exactly how to make a histogram, because really I will have you do that on a test, and I don't really want you to do it. I know that's really lame, but I don't want you to do it with a computer. Okay, so the last one then is I want you to think about confidence intervals, because confidence intervals actually relate a whole bunch to quality. So what we're going to do here is it says, suppose a student measuring a boiling temperature of a certain liquid observes the readings, blah, 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 on 6 different liquids, and he calculates the mean to be this and standard deviation to be that. This 1.2, mean is this, and the standard deviation is this. What is the confidence interval of the population mean at 95% confidence? So we often use this 95% confidence. Now what that means is that we take this one sample, which is x bar up here. This is x bar because it's of a sample, not of the mean. And we want to know how confident are we that for the population mean, which is mu, is between some interval. So 95% confident that it's between some interval, given that we took a sample, this sample. So a 95% is a z of 1.654. Again, I took it from a z calculator, but it's looking at this and saying 95% of the 95% of the time it'll be below 1.645. So that's what it is, like 1.6.5 times that. So what we need to do to get a confidence interval, we take the mean, which is 101.82, plus or minus 1.645, which is the z value at 95%, times the standard deviation. And that means that the real mean, we think, is somewhere the mu, we're 95% sure, the mu is between 99.8 and 103.8, given that this is the sample. It's a kind of a large range, right? But it's because we didn't take very many data points on that. So that's what we came up with. So I hope that helped a little bit, this explanation from this, and we'll be doing more of these.